Picture a fortune teller who has mastered an unbeatable technique. You prosper, she foresaw your success. You suffer, she warned of hidden obstacles. Her readings are never wrong, and that perfect accuracy is a massive red flag. A theory that bends to fit any possible observation has, in a strange way, stopped saying anything about reality at all. By accommodating every outcome, it surrenders the right to be surprised, and ultimately tells us nothing. A young man named Karl Popper noticed this exact flaw in early 20th century Vienna. He watched the grand political and psychological movements of his day absorb every contradiction as brilliant proof of their own doctrines. Then there was Albert Einstein. Einstein didn't offer a flexible prophecy. He calculated exactly how much the sun's gravity would bend starlight, offering the world a specific number. He effectively said, "If the sky does not match this exact calculation, my entire theory is finished." Genuine knowledge lives or dies by its vulnerability. A claim only deserves the name scientific when it offers the world a clean opportunity to prove it wrong. Popper gave this standard a formal name, falsifiability. This vertical line represents Popper's standard, and it operates like a binary switch. Does a claim expose itself to refutation? It's a simple yes or no. Science goes at the top, pseudoscience at the bottom. Looking at this graph, we can plot strict astrology at the absolute bottom. It risks nothing. A highly testable hypothesis in physics goes to the very top. But what happens when two theories both survive this test, yet one feels significantly more useful and informative than the other? Popper drew an elegant boundary to keep out the noise, but a single line turns out to be an incomplete map for measuring the actual depth of what we know. Imagine you are handed two machines that predict tomorrow's weather. Both make precise, testable forecasts. If it rains when they said sun, they're proven wrong. By Popper's standard, they're equals. Open them up, though, and they work entirely differently. Machine A uses the basic laws of atmospheric physics to compute the weather. Machine B can only make a forecast if you feed it the exact starting position of every single atom on Earth. Philosopher Boris Kriger suggests we look deeper, asking whether the theory's laws actually contain enough information to settle the outcome on their own. Kriger calls this metric simulability. It measures how much explanatory power comes from a system's internal rules, rather than relying on impossible-to-measure starting conditions. We visualize this by adding a horizontal axis. Unlike the falsifiability switch, simulability is a dial on a sliding scale. As a theory moves right, it carries the answer within its mechanics, minimizing dependence on the random lottery of how things started. Think of a low simulability theory like a perfectly still pond. Drop a leaf on the surface, and it stays exactly where it landed. The final position is entirely a record of the initial condition. The laws of the water contribute almost nothing. Now compare that to a rushing river. Drop a leaf anywhere in the current, and it gets swept rapidly to the exact same destination. The specific spot where it entered the water barely matters. In physics, this is known as a system forgetting where it began. The underlying laws wash away the initial differences, driving every starting point toward a single inevitable outcome. The most powerful scientific models are rivers. Their final destinations are written into the rules of the system itself. Bringing this back to our coordinate map, we can see that the deepest, most robust scientific theories must score high on both axes. They are highly falsifiable and highly simulable. You can observe this top right quadrant at work in the natural geometry of a soap bubble. These interconnected walls don't calculate their shapes, yet the physical laws of surface tension drive them to this exact geometry, meeting in threes at precisely 120-degree angles, regardless of how the bubbles initially clumped together. Contrast this with the modern internet age, which is flooded with confident, unsinkable claims that explain everything and predict nothing. Therefore, they score a flat 0 on both of our coordinates. Scientific knowledge is not held in place by one clean line. It relies on overlapping coordinates. Learning how to locate an idea on this map, demanding both vulnerability and internal logic, is a basic skill for maintaining an open mind.